Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture 9. Students, in this lecture inshallah we will discuss about the design of shear or shear design. Okay. So before we start the design, I want to share with you some videos. Okay. Watch this video. A shear loading, a 2-point loading, or you can say 3-point loading is applied, and you see the shear failure. Okay, you see now the shear crack in this video, that how a beam fell in shear. Okay, this is very important video, and you must watch this video. Okay, you will understand. You see the crack will be somewhere. Okay, you understand that how this crack is basically developing. Remember, from the support you see this crack is basically occur at a degree of 45 degree, and here as you see. Okay, so this is how we call shear crack, and the crack which is right developed here are called flexure cracks. Remember, but these are shear failure, remember. And you see now very accurately that how these cracks basically it propagate from the support face toward the loading, and it basically the critical section which is basically to be taken out from the face of the support at a distance of d. Remember, that is the most critical section. Okay, so you must watch this. Okay, so this is very important. Clear? This is very important that you understand the crack. Okay, you see the crack is now increasing in width. Clear? And right, see you you see this one. Okay, so this is basically shear crack. This is basically shear crack, and we considered a critical section for shear at a distance of d. Remember, at a distance of d from the face of the support, that is the most critical section. Okay, and this is basically shear crack. You see how it develops when the cracks looks like in this fashion. So student, basically you see here flexure cracks. Okay, this is important. This is very important video. Okay, you people can watch. Look it to the flexure cracks, how it develops. It basically develops at the center line. See, these are the flexure cracks. Remember, and these are very important. Okay, they are producing in the middle portion of the beam. Remember, so that's why the middle portion is very critical for flexure, and the ends is basically critical for shear. You see these cracks and now looks like a shear cracks because they are inclined, and these are your flexure behavior flexure cracks. Okay, this is very important to discuss. Okay, now I want to share with you one of my personal which I observed the shear cracks. Okay, you see here that this is the beam and it is flexure fail, it is bend. Okay, and this is one of the projects which we are working. This is the beam, that beam is also crack, this beam is also crack at the middle. So this is flexure crack, and that is due to poor designing, you can say. I will share this design of this beam as well as the whole detail. Okay, and this is basically, now you see the other beam which is also flexure fail, and the flexure cracks are basically developed. You see here at the middle portion, right in the middle portion you see this crack. So this is how we call flexure failure. So the detailing, the flexure designing of the beam is very important. Okay, if you make any kind of mistakes, you will then face this kind of situation. Okay, so this is very important. You have to properly detail the structure, you have to properly design the structure, and if you want to become the master of your proper detailing, okay, you have to watch those lectures, 18 lectures for detailing, because if you don't understand the detailing, you can't be able. This is the side view. Okay, You see the flexure reinforcement, which is in the bottom, the top two supporting bars, and you see the shear reinforcement that has the stirrups. Similarly, you see the negative reinforcement right here at the supports, like this one. This is for extra bars, which is provided for negative reinforcement. And you see the stirrups are close in this region while they are away, because the shear capacity, as you see in videos, is more in this support region, while the flexure capacity is more in the middle region. And one thing you must make sure that the spacing of stirrups you see here is close, while there is a wider, but it is not necessary that almost shear reinforcement will be close here and will be wider here. Now it all depends upon your design. And you see that in the present design of B2 B1, basically you see I will provide uniform spacing, not this kind of spacing, because my shear capacity is of my section is more. Okay, so that's why I have to use my uniform spacing. Okay, so you see the negative reinforcement which is provided at the support throughout the section. Okay, and no hooks is basically provided, so no need here, but at the end you see here, okay, the hooks, you see the hooks are provided, and here you see, clear. So this is how we say shear reinforcement, clear. And you see the flexure design, flexure reinforcement as well, clear. And these are very important videos you need to watch, but remember the right one. There are many people who do not know about the basics of this kind of reinforcement. Okay, and they teach you the not the right way of detailing and something like that. Okay, if you watch my playlist, basically here here I point out the different errors which those people make. Okay, and I suggest that you must watch these videos in this PRC 1+2 courses if you want to become the master. Now let's proceed to the design. The shear design is simple. We already calculate this. Okay, this is basically 8.808 or 81. Okay, I calculate this in lecture number 7, I think so, and I also calculate this one, I also calculate this one. Now I have to find out basically what I have to find out the shear value VU1. So from similar triangle rule you can easily determine VU1. Simple is that you know about the distance. This distance is 8.81, and this distance will be how much? This distance, now from 8.81 you need to subtract D. Okay, D, and D here is 15.5 inch. Why it is 15.5 inch? Remember, although D value is 15 inch, but here the value is changed. Remember, we provide one layer of reinforcement, and that is number 6 bar. So I keeping basically here I am providing number 4 stirrup. Okay, so number 4 stirrup, I basically when I calculate the this clear spacing is my 1.75 or some 1.5 inches. So number 4 and number 6 bar. So when I subtract all these things, okay, I got my D now is 15.5 inch. Remember, you have to check this. Okay, it will changes when you placing your bar. Initially we assume that we will using this bar as number 8. Okay, so that's why now my depth increased. Okay, and I calculate VU1. That is simple. By similar triangle rule, VU1 divided by this distance, and this distance will be how much? 8.81. Let me write down VU1 divided by 8.81 minus D, that is 15.5 inch divided by 12. Okay, equals to what? Equals to 23.8. okay, 23.83 divided by whole distance, that is 8.81. Clear? Here you from this calculation you got VU1, and that is 20k. Clear? Similarly from that side, because here is the 27. Okay, 15% more shear here. So By similar triangular rule, you got VU2 as well. And for this is for end span, and for middle span, you see the same shear, same support. Remember, same support, and I have already show this diagram here. Here you have, okay, I for end, and this is for middle span. So here my R1 is a what, 23.83, and same R1 here, but only this in this end panel the shear value, this value is 27. Clear? So you don't need to be confused. Okay, if you have any question you can ask. Again, by using similar triangular rule, I calculate VU1, okay, and for this central span VU1 equals to VU2 because shears are same, so 20 kip. I find out my shear capacity of my concrete, that is 2 pi fc prime bd. Okay, this is defined by the ACA code. I got 20 kk, and already you see my shear value is almost 20 kip. 23 is almost equals to 20 kip. You see, this is almost equal. So that's why I don't need to use closer spacing of stirrups, okay, because the shear capacity of my concrete section is more, okay, and that is the beauty of how effectively we select the design, the depth of the beam, okay. Now, so providing nominal shear reinforcement, and we will now providing nominal shear reinforcement. So let's say we are using number 4 stirrup, my AV, that is the vertical, okay. AV is nothing, it is if you are providing, for example, number 4, so the area of number this one and this one, so the area, we have two legs which basically play its role in taking shear. If I show you in this video, okay, you see these stirrups, okay, you see these stirrups, so it has 2 legs, basically the cracks which is developed in this pattern. So both the legs of that stirrup controlling this crack, so that why we use 2 times of area of that stirrup, okay, that is the reason, okay, we use 2 times 0.2, that is my shear reinforcement area. Using the spacing formula, you all know about spacing shear design, so this give me maximum spacing, that is 40 inch d by 2, okay. You have to use these formulas when, remember, when your VC or VS basically is less than 4-5 times FC prime PT. Clear? And already VS or VS, let's say VC is lesser than this value, so that's why we are using these d by 2 and 24 inch. If it is more than, so then this will be d by 4 and this will be 12 inches. I will share this design inshallah. So we got 40 inches, 7 inches, and here we are at 24 inches, so we have to select minimum. We do not use that formula, remember, S is equal to AV Fy and D divided by Vs, because already our Vs is close to Vc, okay. So that's why our Vs, you can say our Vs is because Vs is what, Vs is nothing, it is just only Vu minus Vc by Vc, sorry. So although my Vu is close to by Vc, therefore my Vs is approximately equals to 1 or 0. It is very minimum value. If you calculate this S, it will be more than this spacing, 40 inches. So we don't need to use this one. We have to check these limitations, and this one will cover it. Okay, 7.7, I use 7 inch center to center. So that is the reason that here I am showing you the shear reinforcement. The first stirrup will be placed at a distance of S by 2, and here as well. Okay, and the rest of the spacing of the shear stirrups will be same. Number 4 at the right of 7 inch center to center. So you see in this video, basically the stirrups are close at the support. The stirrups are close at the support and wider at the middle portion. So that why basically here I am using the uniform spacing. And one thing you must make sure in this video, you see here that the hooks which is provided to the stirrups, they must be alternate. Remember, must be alternate. One hook is here, this one will be continuous, and the hook will be provided to this stirrup on the other side, and then this side. So this is how we alternating the stirrups, okay, hooks. And the picture which I show you here, this one, clear? So you must remember, this is very important. So this is the basically the shear design, okay. The stirrups are how they are provided. And one thing I want to share with you here, okay, this is the Nelson book. You see, V is when less than or equals to 4 FC prime, so then your S max will be calculated from these 3 formulas, okay. You 4 formulas. In these 2 you have to select the minimum one, and S max will be D by 2 and 24 inch. But remember, when your Vs is greater than this one and less than 8 FC prime B D into D by 2, then you have to use D by 4 and 12 inch. And if your Vs become exceeds 8 FC prime, then you have to revise your design, okay. You have to revise the design. So that is the way. And one thing which I want to share, if you watch my channel playlist, basically in that channel playlist, PRC2, PRC1 and PRC2 course, this is lecture number 12, which is basically explain the whole design of T-beam when you have subjected to UDL as well as you have point loads, and then how you can control your shear design. So I thoroughly explained that example with all actual cutoff point, bending of bars, actual calculation, not by L by 3 and L by 4, okay. So this is very explanatory video. Remember, this example is basically covered from Nelson book, so please don't miss to watch this lecture, okay, if you want to understand basically the shear and flexure design. Here next is basically is the design, flexure design, and a B2, beam B2. So the procedure is simple, okay. Here we have simply supported beam. So the simply supported beam is quite simple. It is not hardened for us that how to design a simply supported. Your simply supported beam here, okay, one is here, one is here, and one is here, and one is here. We have 4 B2 beams. So the span is basically, the clear span is 18.87, that is panel A transverse width, or LA. And you see 18.875, and we have only one coefficient, that is 1/8. One thing is which I want to share, very important, and that is the this table. This table is taken from Nelson book, okay, and these explain the deflection control, okay, for a concrete beam, okay. You see, for solid one-way slab and for beam, okay. So the coefficients I already explained that I will show you those coefficient 1/11, 1/10. So these are sorry, not those coefficient, this is used for finding the thickness of the slab, okay. So I use this one in the B1 beam design, L by 18.5. Because remember, when one end of the beam is continuous, okay, we use this one. If we have 2 ends continuous, remember, we have a beam, okay, which is passes more than 2 supports. So here this end is also continuous and this end is also continuous. So then we use this L by 21, as well as we use 18.5. We use both these two, and we select the major or the larger value of these two. And if you have a cantilever, then you will use L by 8. So these coefficients are very important. You must memorize these things, okay. Here we have the movement coefficient is 1/8, WL square by 8, okay. The same depth is maintained, okay. You will be uses. Loads are the same, okay. That's load 0.2, and that is the slab above rib weight, okay. Already we calculated. And here we have basically what we have basically, you see, we have panel A. Now panel A is basically, you can say, here this dimension is smaller as compared to this one, and we have C. So here the distribution will be looks like in this way, okay, will be in this way. So the panel A loading will be, you can use this diagram as well, follow the same procedure as I explained in lecture number 7-6, okay, and do the rest of the calculation. Let me show you the rest of the calculation. You see slab load from panel A and C. Remember 1.04 from panel C and 1.46 from panel A. How these we got these? Remember 1.04 is nothing 39.44 divided by 2 times 1 divided by 19. That is the width of panel C, 19, transverse width. I already explained this, 1.04. And you see here is my panel A. Basically let's say I assume that here is my panel A, okay. So this width, that is 19, and you see 39.44 because 39 is total load of the panel, so they will be distributed in this direction and this direction, clear. And similarly 1.46 is explained, that is 55.4 divided by 2 cross 1 over 18. This is 55.4 I explained in the beginning of lecture 6, I think so. So here you see 55.4 which is transmitting in 2 direction, and similar 22.6 in the shorter direction, clear, in the shorter direction, remember. And I have to divide this by the lateral side, okay, because this there we have a beam, okay, here we have a beam. So if beam is here, so this load is coming and I have to use this A length, LA, and LA is 18.87, clear. So that's why I got 1.46. I add up all the loading, this one 2.5, and this is the beam rib weight, this is the beam over the this is the slab weight over the beam, that is 2.94, so a little bit greater value. Moment, I got this moment, okay. My length is basically nothing because this is simply supported. I will use effective length, so not clear length. So 9 by 12 mean that I have to provide 4.5 inch bearing to here, this point, and 4.5 inch bearing to this, because when I using 1 over 11, 1 over 10 WU ln square, so in that we use clear spacing, but here we will use effective spacing, okay. So that's why I'm calculating 19.625, okay, and I plug this value here and I got 1698. So when I design for this moment, I find out basically the BF, okay, that may be center to center distance, there may be L by 4, or there may be this one, okay. And you got this one, and the next one is your MU, BF and D, okay. This is positive moment, so you have to check T beam analysis or rectangular beam analysis, okay. You use the same formula, all the values are known here. The D is 15 inch, okay, 15.5 inch, remember. And because here I'm assuming that I am using number 6 bar, so that's why 15.5. And the first, when I designing B1 beam, so we don't know whether we are using number 6, number 8, so I assume number 8 bar, so that's why I'm using 15. Now I'm sure that I will use number 6, so that's why I'm using 15.5 inch 3 number 8 bar. Now here you see I using number 8 bar, so number 8 bar you have to recalculate your D, okay. And here you see from the calculation he got 15.5, okay. This is 18 is total depth, and 2 is basically the, you can say, the clear spacing. Remember this spacing is, let me show you. For example, if I placing bar here, okay, and I have to use number 4 stirrup, okay. So to the face of the bar, not to the face of the stirrup, that is 2. To the face of the stirrup is this 1.5, okay, that is clear cover. Now I am using to the